A machine built from light, no superconducting circuits, no cooling system dragging temperatures to fractions of a degree above absolute zero, reportedly manipulated 3,050 photons simultaneously across a network of more than 8,000 optical pathways. That's roughly 10 times what its predecessor managed. And the team at the University of Science and Technology of China says classical computers cannot replicate what it just did. Before you write this off as another narrow lab benchmark engineered for headlines, stay with the question, because the interesting part isn't whether this specific result is bulletproof. It's what it reveals about a bet that most of the Western quantum industry quietly stopped making. The superconducting path, Google, IBM, the whole cryogenic ecosystem has absorbed billions in investment and talent over the past decade. Photonics was supposed to be the long shot. Jiuzhang 4.0 just made that long shot look like it's still in the race. And that changes the calculus for everyone betting on who builds the first genuinely useful quantum machine. By the time this is done, you'll understand what Gaussian Boson sampling actually is and why it's hard, why photonics is a genuinely different gamble from superconducting, and what it would take for either path to actually win. You'll also get an honest answer on whether this result, impressive as the numbers are, changes anything that matters. Because this isn't really a story about one machine. It's about two competing answers to the most important, unsettled question in computing. Which physical substrate gets you to useful quantum computation first, and who's still in the running to answer it? There's also a question you should be asking right now. If this machine computes with light and doesn't need exotic refrigeration, why isn't everyone building this way? Hold that. And there's a second question underneath it, because GBS advantage claims have been challenged before by classical simulation researchers who found the earlier numbers didn't hold up under scrutiny. That history matters here. And then there's the money question. PsiQuantum has reported raising over $700 million to pursue photonic quantum computing. What exactly are they betting on that Jiuzhang is already doing differently? Those three questions have answers. They just require building up to them. Start with what the machine actually did. 3,050 photons, 8,176 optical modes, 1,024 squeeze state inputs. Those are the numbers the team reports in its preprint, and they represent a roughly tenfold jump over the previous generation. To feel what tenfold means here, consider that the classical simulation cost of Gaussian Boson sampling doesn't grow linearly with photon number. It grows in a way that makes each additional photon exponentially harder to fake on a conventional machine. The earlier Jiuzhang results drew serious scrutiny from classical simulation researchers. At this scale, the team is claiming the classical wall is even further away. The task the machine performs is called Gaussian Boson sampling, and it needs a concrete picture before the numbers make sense. Imagine dropping a marble into a vast pegboard. Thousands of pegs arranged so that where the marble lands depends on how it interferes with every peg it touches on the way down. Now imagine dropping 3,050 marbles simultaneously, all interfering with each other across every pathway. Tracking every possible route of every marble, all at once, is what overwhelms classical computers. The machine doesn't calculate the answer, it just runs, and the answer is where the photons land. Squeezed light is the quantum resource that makes this work. In normal light, the quantum noise in, say, the amplitude and the phase of the light wave obeys a certain balance, a floor you can't go below. Squeeze states compress that noise below the standard floor in one property at the cost of amplifying it in another. The result is light that carries quantum information in a form the interferometer network can route, interfere, and measure. 1,024 of these squeeze state sources, feeding into 8,176 optical pathways, is a serious engineering achievement just as a hardware problem, before you even get to whether the advantage claim holds. And right now, this specific machine is not useful for much directly. It does one thing, this sampling task, and it does it in a way that's classically hard to simulate in principle. Whether it's classically hard to simulate in practice is a separate question, and it's one the field has been actively fighting about since the original Jiuzhang result in 2020. The programmability question comes next, and it's where the real cost of the photonic path shows up. Here's the thing nobody advertises about building quantum computers with light. Photons don't interact with each other. In a superconducting quantum machine, you can engineer what's called a 2-qubit gate, a controlled interaction between two quantum bits that lets you build up arbitrary computations. With photons in a linear optical architecture, getting two photons to interact reliably and on demand at scale is a hard, unsolved engineering problem. This is why Jiuzhang is purpose-built. The optical network is set up in hardware. You run it. You measure. You cannot reprogram it mid-computation the way a general-purpose quantum processor would need to be reconfigured. It's extraordinarily precise at one thing, but you can't rewire it between tasks. Photon loss compounds this. Every additional optical mode, every additional pathway across which a photon might travel, increases the probability that the photon simply doesn't arrive at the detector. At the scale of 8,000 modes, managing loss is not a minor engineering footnote. Specific figures for Jiuzhang 4.0's loss rates haven't been published in the materials available here, but photon loss in optical systems is a fundamental constraint, and it scales with the network. So why bother? Because the superconducting path has its own enormous burden, a refrigeration infrastructure that must cool chips to within a tiny fraction of a degree of absolute zero. Temperatures colder than the vacuum of outer space. Building, maintaining, and eventually scaling that infrastructure is expensive, complex, and doesn't obviously get easier as you add more qubits. Room temperature operation, if you can solve programmability and loss, is a massive long-term structural advantage. That's the bet. The question is whether you can actually solve it. This is also where Western photonic efforts look meaningfully different from what Jiuzhang is doing. The University of Science and Technology of China has been iterating specifically on this architecture since the original Jiuzhang paper in 2020 dollars, 4 generations in roughly 5 years. Each generation has pushed the photon count and the mode network further. The result is a machine that is genuinely impressive at this one task. PsiQuantum is doing something else entirely. Its reported bet, built on over $700 million in funding as publicly disclosed, is fault-tolerant universal quantum computing manufactured using silicon photonics fabrication. That means building photonic quantum chips in the same kinds of semiconductor fabs that produce conventional chips, with error correction engineered in from the ground up. That's a radically longer horizon. And Xanadu, based in Canada, has published its own Gaussian Boson sampling results using programmable photonic chips, a step toward flexibility that Jiuzhang hasn't taken. Jiuzhang is like a purpose-built sprint car that just recorded the fastest lap on one specific oval. PsiQuantum is trying to design a car that can race on any track. The sprint car's lap record doesn't tell you who wins the open road race, but it does tell you the engine technology is further along than most people assumed. Now the scrutiny question, because this is where the honest accounting lands. GBS advantage claims have a history. After the original Jiuzhang result in 2020 and the follow-up in 2021, classical simulation researchers, including teams at major Western universities, published work arguing that improved classical algorithms could simulate the earlier results faster than claimed, or that the hardness assumption had been overstated in specific parameter regimes. This doesn't mean those machines weren't genuine engineering achievements. It means the boundary between classically hard and classically manageable is actively contested terrain, not settled science. Jiuzhang 4.0's claim is currently at preprint stage. It has not yet been subjected to the peer review process or the independent counter-simulation scrutiny that the earlier results eventually received. What happened with those earlier results, where the classical competition was real and meaningful, will happen here too. The classical simulation research community will get to this. The distinction worth holding on to, whether this specific sampling result is classically hard, is a separate question from whether the University of Science and Technology of China team can build photonic machines at this scale. The second fact is harder to dispute. The engineering is documented. What's genuinely uncertain is whether the advantage claim survives the counterattack that's coming. So what actually changed? Here's my honest read. The triumphalists are wrong. Jiuzhang 4.0 has not proven that photonic quantum computing has won. The advantage claim is unverified, the programmability gap is real and unsolved, and a general-purpose photonic quantum computer remains far off. But the dismissers are equally wrong. A tenfold photon count jump is a genuine engineering achievement. It keeps a rival substrate credibly in the race. It forces the question of whether Western investment, concentrated as it is on the superconducting path, has been tracking the right horse. What Jiuzhang 4.0 actually did is raise the floor of the photonic path. Not prove it wins, not move the finish line, not answer the programmability question, but prove that this architecture is still running, that it can scale, and that the race between two genuinely different physical bets is not over. Two horses are still on the track. The finish line, genuinely useful, programmable, error-corrected quantum computation, hasn't moved closer for either of them. But the gap between the horses just narrowed. The floor of the photonic path just got raised. Which horse you back now depends on whether you think programmability or raw scale is the harder problem to solve, and reasonable people disagree. Here's what I want your honest read on. Does a tenfold scaling jump in a specialized sampler actually move your confidence in the photonic path? Or does none of it matter until someone shows a programmable photonic machine doing something a superconducting chip can't? Two genuinely defensible positions. Tell me which one you hold and why in the comments. Subscribe if you want to follow how this specific claim holds up when the classical simulation teams get to it, because that's where the real verdict lands. 3,050 photons moved by light. The machine is real. What it decides, that's still open.